Okay, let's take on a new topic associated with thermochemistry, specifically the ideas behind phase changing or changes in state. The three states that matter come in typically are gas, liquid, and solid, which are shown here from left to right. Now what happens in a gaseous state is that the attraction between the different molecules is fairly weak, and this takes place because the motion of the molecules is very rapid, and therefore the attraction between the molecules is not sufficient to hold molecules together and create a liquid or solid. Now if you slow these molecules down, then the attraction between the molecules becomes sufficient to hold those molecules together, so the spacing is minimized. And although the molecules can slide past each other as liquids do, they are unable to lock them into place, and therefore the forces are considered moderate. Then of course the forces can become very strong, and you get a very regular spacing of the molecules to form the solid. The molecules still do have motion, but it's a vibrational motion. Now the IMF, which is the intermolecular force attraction, that means between the molecules, so the IMF strength as it increases, then the temperature at which something melts or boils increases. So if you have molecules that have a strong IMF, they will tend to hold together longer, and it's harder to melt or vaporize the substance because it's harder to overcome those attractions. Now what do we mean by intermolecular forces? Inter means between molecules, not within the molecule. So here we see two molecules on the left and the right, and you can see there's an attraction between the two of them. This molecule is most likely water, and there's an attraction between the negative and positive poles of the molecule, and this becomes the intermolecular forces. And if we use, rather than water, we used, for example, benzene or rubbing alcohol, and then the attraction forces are different, and that will change the melting and the vaporization points. So we see it is a measure of the strength of that attraction. Now there are three ideas here. The boiling point is referred to as the heat of vaporization. The melting point is the heat of fusion. And there is something called the heat of sublimation, which goes directly from a solid to a gas or gas to a solid. And dry ice, which is actually carbon dioxide frozen solid, it undergoes a sublimation directly to a gas. And that's why it's very useful to keep things cold, because unlike ice, which goes through a water state, liquid state, and everything would get wet and soggy, dry ice goes straight to a vapor, and therefore you don't have the risk of things getting soggy as it warms up. Now this sequence is a very important idea. Let's be clear about this. We have solid on the bottom to gas on the top. And what you have is the temperature of that substance increases as you go from the solid to the gas. So a thermometer would read a higher temperature for gas than a liquid or solid. That's also true for the sublimation. It's a straight shot from the solid to the gas. And the terminology which we've discussed, which is from solid to liquid is melting, liquid to gas is vaporization, condensation as you go from gas to liquid, and freezing is from liquid to solid. Now a very important point here is notice the amount of temperature, or in this case the amount of energy that is required for a solid to melt to a liquid is in fact the same amount of energy to go from a liquid to a solid. So the amount of heat, the Q value, the amount of thermal energy required to melt or freeze is exactly the same. It's just a difference in whether the heat enters the system, which is melting, or the heat leaves the system, which is freezing. And the same rules apply liquid to gases. The amount of energy required to vaporize a certain amount of liquid to a gas, or to go from a gas condensing down to a liquid, the amount of heat is exactly the same. It's just a difference in the direction that it's moving. Notice that the reverse of sublimation is referred to as deposition. It goes straight from a gas to a solid. Now again, the ideas we're about to review here are very important to keep in mind. The solid is considered very orderly, much like a crystal might be considered. And a gas, with all the molecules moving around wildly, has the least amount of order. Now, to go from a orderly solid to a disorderly gas, you have to input energy. That's referred to as endothermic. So the container that has the, let's say, ice in it, you have to add heat to that container. You have to add heat to the ice to get it to go to gaseous. And when the system, namely what's inside the beaker, when that system requires an input of energy, we refer to it simply as an endothermic reaction. And of course, the reverse is true. To go from a gaseous state, which is not very orderly, and go to a more orderly state, such as a solid, that's exothermic. In other words, the system has to remove heat from itself to allow it to move to a greater order or move to a solid system. So endothermic, the system has to be gaining heat. Exothermic, the system has to be removing heat or losing heat. Now here's kind of a summary of what we've just looked at. It's a very busy diagram, so let's try to take a look at how it goes. If you look on the lower left, that's solid ice. Notice how orderly all the molecules are, and that's because the intermolecular forces, the IMF, is strong enough to hold it in an orderly environment. Notice then, as you move from left to right, the plus means heat is being added to cause the motion to increase, and the IMF, or intermolecular forces, are not strong enough to hold those molecules in an orderly situation, and they begin to move around, slide past each other. We now have a liquid state. But all of that took the addition of heat, so that was endothermic. If you went from right to left, liquid to solid, we have to dump the heat energy. We have to remove heat to allow the orderly bonding of those molecules of water to take place. Then as we move from the liquid to a gas, from the right side up to the middle, notice that what we have happening if we go plus is evaporation, and notice how much spacing now exists between those molecules. To create that space requires the input of heat, and therefore vaporization or evaporation is an endothermic reaction. That's why it's a plus there. Notice what's happening is the hydrogen bonds, as illustrated on the right, are not strong enough to hold together the molecules because the thermal heat is so great. The reverse is true, of course, is the condensation. Final point from this is to notice the water molecule when it's all by itself, how polar it is. That means there's a concentration of electrons in one zone, which is near the oxygen, and that means there's a positive concentration of electrons on the other end. And it's that polarity, it's that regions of positive and negative that create the degree of attraction between the molecules, and therefore affects the amount of energy you have to pump in to create that separation. Obviously, there's a sublimation or deposition that does take place going back and forth. Now, the idea of latent heat is a very important idea. We list it as the delta H of fusion, and what it is, it's the energy that is added or removed to create a melting or a freezing process. Now, let's give some examples of this. Notice that the melting point of argon is minus 190 degrees Celsius. So it melts at a very, very low temperature. But the reason why that's true is because the delta H of fusion, which is the amount of attraction between the argon atoms, is very little. It only takes 1.3 kilojoules per mole of argon to melt it. Now, if you take a look at benzene, benzene's melting point much higher. It melts at 5.5. But notice that the delta H of fusion, meaning the amount of heat it's going to take to separate or pull apart solid benzene and melt it, is 10.9. So the attraction is greater than it is for argon, and that's reflected in the fact that benzene has a melting point that in fact is much higher. So the heat of fusion is the amount of heat it takes to separate solid molecules from each other, and if the heat required is not very high, it tends to have a low melting point. Now, this delta H of fusion is also referred to as latent heat. What that means, it is the heat that becomes stored when it goes from a solid to a liquid, or it's the heat that is released as it goes from a liquid back to a solid. And so that heat is referred to as latent heat. The equation is that the Q, which is the amount of heat or latent heat involved during a change in state, in this case solid to a liquid, which is the delta H of fusion, is m delta H fusion. Now the equation here lists the calories per gram or joules per gram, but it also can be listed as calories or joules per mole. And so depending upon the calculation you are being asked for, you would need to know whether it's in joules or in moles. Now again, melting requires the system to gain or increase the amount of Q, and therefore Q is a positive value. Freezing, there is a loss in heat, so it's a negative Q. So notice the positives and the negatives are relative to the movement of the heat in or out of the system. Now, what about vaporization? What causes, in this case, what causes the roll boiling? What happens during vaporization is the molecules that are in a liquid state, the intermolecular forces are able to hold the molecules relatively close to each other, though they can slide around. But suddenly what happens is the amount of vibration is too great, and there's a pocket where a whole bunch of the molecules have a jump in their spread, a jump in their spacing, and when it does that, it turns to gas. And that gas shows up as a bubble, in this case of steam, that is surrounded still by water molecules in a liquid state, but that bubble is of steam, and it almost always takes place towards the bottom of the pot because that's where it's hottest. And what happens is this bubble of steam gas is less dense than the surrounding water, so it quickly rises to the top where it bursts and it dumps the steam gas into the surroundings. So it does require enough thermal energy to cause that separation and create the gaseous state at the bottom. Now what you see here is that different substances boil at different temperatures. And the reason why it boils at different temperatures because the molecules have different degrees of attraction between them. So for example, you'll notice that diethyl ether, it boils at 34.6 degrees Celsius. So it boils at a relatively low temperature. 34.6 is a little bit higher than room temperature, maybe about 10 degrees higher than room temperature. And so one might imagine at room temperature observing a boiling liquid, that would be diethyl ether. And the reason why that's true is those molecules do not have a particularly great attraction to each other, and so you see it boiling. Ethyl alcohol is higher than, of course, water, which you need to know. Water is going to boil at 100 degrees Celsius. Now take a look at the very bottom there. That's ethylene glycol. It boils at a very, very high temperature because the attraction between the molecules is very great. Now whenever you do a study of boiling points of a liquid, it has to take place at what's called standard pressure, which is considered at sea level. If you change the altitude that you are working with, then in fact the boiling point will change. But in this case, we assume it's a standard value, which is at the sea level, and now you can compare boiling points for different substances. Now what happens, as I was saying, is as you go to less and less air pressure, which means you go to a higher and higher elevation, you'll notice the boiling point gets smaller and smaller. So what this means is at 9,000 meters, the boiling point of water is 70 degrees Celsius. If you go to the top of Mount Everest and you boil water, while it's boiling, you can stick your finger in the boiling water and have no harm done. That's because the boiling temperature is much lower at a higher elevation. And the reason for that actually is based upon the rules of gases, which we'll be taking a look at. Condensation is when the vapor turns to a liquid state, and the condensation that takes place on a cold bottle is because the surface of the bottle is colder, and when the gaseous material, say the gaseous water that's evaporated on a hot day, when it comes in contact with the cold surface, the speed or the motion of the gas water vapor slows down to the point that the attraction between the molecules becomes greater than the speed of the motion, and you see material condense into a liquid on the outside, and that causes the condensation on a hot day. Just as there's latent or stored heat during the freezing process and melting process, the same is true for vaporization. The latent heat of vaporization is calculated with the same equation, although the actual delta H value is going to be different. And here again you see it listed as grams. It could also be listed as moles. Boiling, the system is gaining heat, therefore the Q value is a positive, and condensation is the negative, and so it's losing that heat. Now this we've discussed in class. It's a heating and cooling curve, and let's make sure we walk through it and understand it. During the solid stage, moving from left to right, during the solid stage, heat is going in and the temperature is rising. However, when it reaches a certain point, heat is still going in, but that heat is going to latent heat. It's going to the phase change, and therefore there's no temperature change, which is point A to point B. Then point B to point C, the heat going in is changing the temperature, vibration. We see a phase change from C to D during the boiling point, and finally the vaporization. That's a heating curve because you're gaining heat along the way. What's happening is there's an increase in the amount of heat energy being dumped into the system. And you again see that the temperature doesn't change. Now, there is something called cooling curves. Cooling curves, of course, means heat is being dumped from the system. Once again, you do have an output of energy. Temperature still remains constant. And it's the same idea as a heating curve, just in reverse. When you calculate the amount of heat change, remember, from point up to point A, that's going to be a specific heat. Then during the phase change, that's going to be the latent heat. Then you have specific heat. Then you have latent heat or molar heat. You can use both those phrases. And finally you have the specific heat here. If you want the total heat, the total amount of enthalpy, the delta H is simply the sum of all those items. Water is a very important idea. It has a unique property, which is when it forms the solid, it is less dense than the water itself. And because it's less dense, it floats. So we see here that if you map the density, when the temperature is greater than 0, which is actually at about plus 4 degrees Celsius, the density of water is the greatest. But as in fact it moves less than 0 and turns solid, the density gets greater. That has to do with the fact that in fact the molecules, as it forms a solid ice, actually slightly spread out, causing it to be less dense. And it's crucial because now the ice will float. If that wasn't true, then the ice would obviously be sinking and we couldn't have liquid water on the surface of the earth. So water has unique properties. It's colorless, odorless, tasteless. It's the only inorganic compound that exists on Earth at Earth temperatures, normally as liquid. 65% of all of our body is made up of water. It what fills the cells and allows all the chemical reactions to take place inside it. And because of its very high polarity, it allows for it to dissolve many, many things. And also it boils and melts at very high levels, relatively speaking, because the polarity of the water, it holds itself together, it requires a lot of heat to go in. And finally, because the unique properties where it lines itself up as a solid, it's less dense as a solid, and therefore it floats. Let's end it there.